3.1 Intermolecular forces. What are intermolecular forces? Intermolecular forces, or IMFs, are the attraction between atoms, ions, or molecules that hold them together. There are 6 different types of IMFs: London dispersion, dipole-dipole, hydrogen bonding, ionic, metallic, and covalent networks. The last two are not technically IMFs as they are intramolecular forces. They all differ in the arrangement of the electrons. How to determine what type of IMF? Start by identifying the types of atoms in the sample as either metal or non-metal. If a sample has a metal, then it is either ionic or metallic. If it has no metals, then it is either London dispersion, dipole-dipole, hydrogen bonding, or covalent network. For example, we have NaCl down below, which is a combination of a metal and a non-metal. Thus, the structure below has ionic IMFs. London dispersion forces, or LDFs. London dispersion forces occur in all substances and should always be considered. They are the only type of IMF present in nonpolar molecules. At any given time, one nonpolar molecule might have more electrons on one side than the other side, making it polar. For that instant, the molecule would have a partial negative side and a partial positive side, and it creates a temporary dipole. The molecule with a temporary dipole then induces a dipole on its neighboring molecule, creating a London dispersion force between the partial negative side of one molecule and the partial positive side of another molecule. This can be seen on the image to the right, where the molecule on the left induces a temporary dipole on the molecule to the right. Dipole-dipole interactions. Dipole-dipole interactions occur between polar molecules. The attraction comes from the partial charges that exist on opposite ends of a dipole. They are similar to LDFs, but are much stronger due to occurring because of a permanent dipole. Since these interactions occur between polar molecules, the more polar the molecule, the greater the dipole-dipole interaction. Additionally, the shorter the distance between the two dipoles, the stronger the dipole-dipole interaction. Hydrogen bonding, or H-bonds. Hydrogen bonding is not a bond, but a dipole-dipole interaction that only occurs when a hydrogen atom is directly bonded to an F, O, or N, in or outside of a molecule. These attractions are incredibly strong, so the boiling point of molecules with hydrogen bonds is very high, and the amount of energy needed to break the bonds is high as well. On the image to the right, you can see H bonding occurring in human DNA. Ionic. Ionic attractions occur between metals and nonmetals. In this interaction, one atom will lose electrons to complete its valence shell, usually the metal, and the other atom will gain those electrons to complete its valence shell, usually the nonmetal. Overall, ionic is stronger than dipole-dipole, hydrogen bonding, and LDFs. An example of ionic dipole forces is when Na bonds to Cl to form NaCl. The Na atom will give up one of its electrons to Cl so that they can both complete their valence shells. This is demonstrated in the image to the right. Metallic. Metallic bonding occurs between metal atoms. It can occur between just one type of metal or for different types of metal, creating a mixture called an alloy. The metallic attraction is due to multiple metallic cations being attracted to a delocalized sea of valence electrons. This can be seen on the image to the right. The IMF is stronger when there are more valence electrons and smaller metallic cations. Covalent network. Covalent networks occur between carbon atoms, silicon atoms, and carbon with oxygen, or silicon with oxygen. Specifically, C-diamond, C-graphite, C60, SiO2, and SiC. This is the strongest IMF. The attraction due to many covalent bonds leads to a large macromolecule. On the image to the right, there is a covalent network of diamonds. Properties. This table shows properties and how they are affected by increasing the IMFs. Boiling point, melting point, freezing point, enthalpy of fusion/vaporization, viscosity, surface tension, and latest energy all increase when you increase the IMFs. Vapor pressure and solubility decrease when you increase IMFs. Example problem. Which intramolecular force is responsible for the unusually high boiling point of water compared to other molecules of similar size? The answer is hydrogen bonding. And the explanation is water has LDFs and hydrogen bonding. Molecules of similar size usually have LDFs, but not all of them have hydrogen bonding, which makes water much more susceptible. gives it a higher boiling point since hydrogen bonds are much stronger than LDS. Some extra resources you can use are these two YouTube videos. Thank you.